All right, part two. Say what? Yeah, so I think 520 is all right. Or, or something approximate. All right, so I'm going to continue where I left off, I guess, yesterday. So again, this is some kind of introduction to DT theory. This is the second lecture. So roughly speaking, where I left off yesterday was stating kind of the main conjecture about the relationship between Donaldson-Thomas theory and Gromov-Witten theory. So what that looked like was, so X was a threefold, and then I fixed a bunch of cohomology classes. And then I had two generating functions. So the Gromov-Witten one was a function of U, and this was some kind of sum over all possible genus of my domain curve. And then I had this, I forget exactly my notation, but I had this generating function where I did intersection theory on the Hilbert scheme of curves. Again, we fixed the curve class, but then I was summing over the constant term of the Hilbert polynomial. And then after I normalized it appropriately, the claim is that these two are equal after this change of variables, conjecturally. And part of this conjecture is that actually this thing on the right is actually a rational function in Q, so this kind of change of variables is uncontroversial. Right. So before I go on, I wanted to just say some natural questions you can ask about how to kind of push this conjecture in different directions and to what extent we can say anything. So like in this statement, I think is known in some cases, but not in a great deal of cases, basically. Toric threefolds and things built out of toric threefolds. So you can ask a couple of natural questions. So the first is, well, as YP has already talked about, on the Gromov-Witten side, these are primary invariants. These are things where I just pull back cohomology classes from a target, and I don't do anything from the moduli space of curves. If I wanted to do that, we get some what we were calling descendant invariants. And so the first question is there some natural analog of descendants on the right-hand side, and then is there anything you can say about extending this correspondence? And I mean, it's a little bit surprising that there would be, because the way you should think about descendants is, in some sense, they come from this stabilization map. They're really cohomology classes on the moduli space of curves that you pull back to the space of stable maps, up to boundaries and things like that. And there's no analog. If I have the Hilbert scheme of curves here, there's no analog of a map to MG bar. But there is some analog of what you might guess these descendants would be. So the main thing to remember is, how did I define primary invariants on the right-hand side? And well, to define, so to speak, this insertion in Gromov-Witten theory on the sheaf theory side, I took the second Chern character of the universal ideal sheaf, and I started taking Kunith components of it. And so, well, I don't just have Chern 2, I have a whole bunch of Chern classes. And so the procedure for producing the analog of these kinds of higher descendants would just be to take more interesting, higher degree Chern classes. So this is somehow in your head what you should think of as being the correspondence. Where this thing on the right-hand side is just the gravitational descendant as defined in YP's talk. And so, okay, so at least this is a definition of what you might stick in on the right-hand side. And then you can ask, is there some version of this that's true? And the short answer is kind of. And there's very recently been some work of Alexey Oblomkov, Andrei Kumkov, and Rahul Pandey, where they've at least conjecturally extended just the statement to include descendants, but the statement is extremely complicated. It's not just this kind of simple change of variables and the two things are equal. You get basically some kind of, arbitrarily many correction terms, depending on how big your beta is. So it ends up actually being pretty complicated. And I don't, to be honest, fully understand what it looks like. But there is something that seems to be true. For this first statement, though, so this is really the second part of the conjecture. The first part of the conjecture was just some statement about this expression being a rational function. And that statement seems to go through fine. So I think this was conjecture 1 in my lecture yesterday. So this has a nice analog, and it's just really the nicest statement you could expect, that if I assume my cohomology classes all have positive degree, so let's call this kind of insertion sigma k. Oops. So just the analogous generating function with descendants, once I normalize it, so I always normalize by the Hilbert scheme of points, this kind of expression will be a rational function, conjecturally. It's just that the change of variables, when you try to match it with the Gromov-Witten side, all hell breaks loose. Okay, so this is the first natural thing you could try to do. The second thing you could ask is that, as I've written it, because of this kind of this is an exponential change of variables. So if I'm interested in any given coefficient on the left-hand side, I really don't see it in any given coefficient on the right-hand side. This change of variables is really mixing things up a lot. And so you can ask, is there any way of isolating something a little simpler on either side of this equation? And in general, I don't know the answer to that. But it turns out there is a version of this conjecture that just involves genus 0. So this question is, can we isolate And the reason you would want to do that, again, is that right now, to prove this conjecture, you really have to understand the whole genus expansion on this side, or really the whole chi expansion on the right-hand side. It doesn't seem like there's any hope of, it makes it very hard to get your hands on. And so like I said, I don't know how to do anything like this in general. But if I'm interested in genus 0, and X is a Calabi-Yau threefold, then there is a nice answer to this, involving a different moduli space of sheaves. So I don't know how well known this is, but I think it's actually quite nice. So the setup is, so X is going to be a Calabi-Yau threefold. I'm going to fix an ample bundle. And instead of considering ideal sheaves like I was doing when I defined DT invariance, I'm going to consider a moduli space of torsion sheaves. So I'm going to consider sheaves Q, sheaves a sheaf on X. I'm going to ask for it to be stable with respect to the polarization that I've picked out. And I want, let's see this, so the rank of Q is 0. C1 is 0, C2 is beta, and then the Euler characteristic Q is 1. Okay, so this actually has some beta dependence, which L dependence, because this moduli spaces depend on the choice of stability condition that I've picked out. And because I've rigged things appropriately, this is actually going to be a proper moduli space. There are no semi-stable points because of the Euler characteristics doesn't allow it. And so it turns out one can show that all this kind of virtual class machinery will apply in this setting as well. And I have virtual dimension 0. So I have some kind of virtual dimension of this moduli space is 0. And so I get a virtual class, and I can just take its degree. I'm just getting some number. So I'm putting in the L just because I want to stress that a priori, this depends. So let's see. On the choice of polarization. And the conjecture is that this invariant, this sheaf theoretic invariant, exactly picks out the genus 0 part of the Gromov-Witten potential. So the conjecture, and this is due to Sheldon Katz, is that, well, if I'm interested in the genus 0 Gromov-Witten theory, so this is Calabi-Yau, so it's always just a number. There are no insertions that I need. Well, it turns out there's a nice expression for it in terms of this torsion sheaf invariant. So I take, so if beta is some multiple of an integral homology class, I take all, so to speak, integers that divide beta. I've already forgotten how I've written this. So this is some way, and in fact, I mean, so this doesn't seem so closely related to what I've written down before, but it's actually a theorem of Toda. First of all, that these numbers are independent of the choice of polarization. So first of all, that these numbers are independent of L. Second of all, that if I replace this constant term 1 with anything relatively prime to beta, I still get the same number. So for instance, if I think of these numbers as n beta 1 of L, then n beta k of L are the same. It doesn't matter what this choice of constant term is. But then more interestingly, what Toda actually shows is that the general Gromov-Witten dt correspondence actually implies this statement. So this is some kind of, if I take this expression up there and I kind of specialize to the genus 0 part, which I can think of as being something like the singular behavior of the left-hand side as u goes to 0, then I actually get precisely these torsion sheaf invariants. And so, I mean, a question that I think is interesting is that, I mean, the nice thing about this conjecture as opposed to the general case is that, understanding the genus 0 Gromov-Witten theory is a lot easier for us. And so you can ask, does this mean that there are cases where this conjecture is somehow more accessible? For instance, the quintic threefold. Can we at least prove this conjecture and then worry about the more general case later? And to be honest, I don't really know of any serious examples where this conjecture is much easier. The only example that I can think of where we can at least prove this conjecture but not the general case is when X is a K3 fibration. So let's say a family of K3s over a disk, and I. Mm-hmm. Yes. So this was Sheldon's attempt to define the BPS invariant, some kind of direct definition. Right. And so in this case, at least, if you have, so to speak, if you have a curve in the central fiber which is obstructed, then you can show this conjecture for curves that are in multiples of that class. And so then we know. And we don't know how to do this yet for higher genus. So this is something where at least we can work out the genus 0 case and nothing better yet. Although this actually ends up being extremely difficult. So not easy. Okay. And so maybe the last thing I want to say, so I talked about descendants, I talked about just the genus 0 case. And the last thing you can ask is, I've defined right now the right-hand side using this kind of normalization procedure where I just divide out by the contribution from the Hilbert scheme of points. And so you can ask is there a more geometric way of doing that normalization? And so, and the answer is yes. And the idea is, again, it's similar here. I write down a similar but not exactly the same moduli space of sheaves and run the same series of constructions there. So this is what's called Pondere-Pondé-Thomas theory. And I write about this in the notes. The idea is you look at a moduli space. Instead of moduli space of sheaves, you look at the moduli space of stable pairs. So there's going to be sheaves with a section. And there's some completely parallel set of conjectures that you can make along those lines. And so really, the way I've been doing these lectures, I've really just been focusing on the Hilbert scheme. But really, nowadays when you think about Donaldson-Thomas theory, the idea is you consider moduli of sheaves with all kinds of different specifications. And depending on what question you're interested, one of these might be better suited. Okay, are there any questions?
Is there any way to find a necessity of normalization on the other side, namely like a main function coming out of the Gromov-Witten?
Yeah, you can kind of put it in by hand. So when I defined the Gromov-Witten side, I had this condition that the connected components are always non-contracted. So you could be a little silly and remove that condition and then divide out by it. And then it's true there is some kind of similarity between the Gromov-Witten theory, so to speak, with beta equals 0. There's something kind of superficially similar between that and the McMahon function, but I don't know how seriously to take that. Anyways. The short answer is no, but unless you if you want to, unless you're feeling really speculative or drunk or something. So. All right, so with the time for the rest of this talk, what I want to do is I just want to talk about just some of the techniques we have for actually doing anything with this stuff. And the subject is relatively young enough that there aren't so many. And so the two main ones that work really for all threefold, and not just there are a lot of techniques that are kind of special to the Calabi-Yau case now. But in terms of things that work for other threefolds, there aren't so many, and the ones we have are pretty much stolen from the Gromov-Witten side. But still, I want to talk about them. So the first is going to be localization technique, so equivariant localization. I don't know, let's call this 2. Everything came before it was 1. So, so the geometry here is we want some kind of threefold where we have a nice big group action. So the situation that works best is we say that X is a toric threefold. If you don't know what that is, just you can pretend that X is P3. In particular, that means we have some three-dimensional torus acting on X. It has isolated fixed points, isolated one-dimensional orbits, a dense free orbit in the middle. And instead of doing everything I've been doing before with usual cohomology and homology, you work equivariantly. So you work now with equivariant cohomology of X, equivariant homology of X, etc. And the point is, all of the constructions that we've been talking about are functorial enough that everything actually generalizes to this setting. So we have, instead of a virtual fundamental class, we have some equivariant version of that that will lie in the equivariant homology of my moduli space, and so on. And the invariance we get, instead of just being numbers now, so the way you can think about these invariants is I have some kind of moduli space proper over a point. I was doing some kind of nonsense on M, and then I push forward to the homology of a point, and that in the original case, that was just a number. Now when I do that, I'm going to call this map pi. I'm going to take a bunch of stuff and push it forward. It's going to lie in the equivariant cohomology of a point. And this is a more interesting ring. This is a polynomial ring in 3 variables. And so this is where my equivariant invariants take values in. And so the reason why this is a useful thing to do, is that assuming our torus action is big enough, we can actually reduce calculations just to the fixed points. The Tiabat localization. So this is just a statement first about doing calculations on the equivariant cohomology of a smooth projective variety, or just more general than that. So M is smooth. With the torus action, everything's going to have this torus action, and I can consider the fixed points of this torus action and the inclusion map to M. And then I have a restriction map that will take the equivariant cohomology of M and pull it back to the equivariant cohomology of the fixed point set. Here the torus is acting trivially, so this is something really stupid. And really, roughly speaking, what this theorem says is that this restriction map is actually an isomorphism after I tensor with the fraction field of my ring. So after, once I pass to the field of rational functions. So a priori, these are very different, but once I allow myself to some denominators, they basically become the same thing. In fact, the inverse map is really easy to write down. So there's the formula is I sum over connected components of my fixed locus. So what is this expression here? Gamma is an equivariant cohomology class on the total space. And the claim is it's equal to the following, where I pull it back and then push it forward again after I invert this equivariant vector bundle on the fixed locus. So this is something that lies again, I always have to tensor with the fraction field because I've started putting stuff in the denominator. This is just a normal bundle. So even just for if you've never seen this before, there's a lot of fun just to be had, even in the case of when M is P1 with the usual C star action. Just by playing around with different choices of what gamma is, you get all kinds of interesting combinatorial identities, which I won't have time to do justice to now. But yeah, I mean, maybe I can just say something. I mean, what this, for instance, let's say M is P1. What does this look like? So, well, P1 has 2 fixed points with respect to the usual C star action. So this is going to be a sum over these 6 points. So it's going to be, there's going to be a term for 0 and a term for infinity. And here in the denominator, I'm going to take, well, the normal bundle here. Well, it's just, well, it's trivial, but it's not equivariantly trivial. It has some character, and that character is going to go in the denominator here. Well, here will be something like t, and here will be like negative t. This is very roughly what this kind of formula looks like in the smooth case. And the kind of like unbelievably useful fact is that there's some analog of this formula in this virtual setting. So are there any questions about this? I feel like if you haven't seen this before, this is probably not the best introduction to this subject. So, but I can try to say a little bit more if ever. Oh, you're asking if I somehow have a bigger set of variables?
Yes, for instance, for P3 you have P4, right? But you have, however, considered P3.
Oh yeah, so this behaves in a very natural way with respect to restrictions to subtori. And so if I somehow added in an extra torus that's acting trivially, it just won't show up in any of the formulas. Put another way, I mean, equivariant cohomology behaves in a kind of functorial way with respect to passing to a bigger or smaller subgroup and so on. Okay. So what is the virtual version of this localization formula? So let's say X is now a scheme. And the point is X is now no longer smooth. So a priori it's not clear that anything should work out very nicely. And I have an obstruction theory, which is T equivariant. So there's some analog of this formula that you just can write down blindly. I mean, the naive thing to do is to take this formula and then put virtuals everywhere. And amazingly, that actually is correct. So I'm going to write down a formula in equivariant homology. So what this is saying is that, again, so this is going to be a sum over connected components of the fixed locus. And what it's saying is that actually X carries a perfect obstruction theory, and so does each connected component of the fixed locus. Not only that, there's also some notion of a normal bundle, and I just take the analogous formula in this setting. And so the way I calculate these things, for instance, is that, well, I talked yesterday about deformation spaces and obstruction spaces. If I'm at a fixed point in my moduli space, these are going to be representation. These are going to carry T actions. So I can think of them, I can decompose them with respect to the T action. So there's going to be some kind of fixed part and some kind of moving part. And similarly for the obstruction space. So the obstruction theory for the fixed locus is exactly going to be the fixed part of the deformation space and the fixed part of the obstruction space. And similarly for this normal bundle. So there's some kind of completely parallel story that you can write down. And then you can try to use this formula. So before you were interested in, say, the Hilbert scheme of points on C3, and now you reduce it to understanding what the fixed points are. Okay. And in fact, if you do that calculation, things seem great. So let me just say one thing before I start talking about doing calculations. So maybe I won't even write this down. Is that so? If again I have a torus action on X, everything I've talked about, the Gromov-Witten theory side and the DT side, become equivariant theories now, and just the naive generalization of the equivariant correspondence goes through perfectly conjecturally. There's all the evidence we have suggests it's true before I start putting in descendants. But as long as I'm not putting in descendants, everything seems completely beautiful if I'm just doing these primary insertions. Just the exact same statement I wrote on the board yesterday applies. Okay. Let's get more, let's just see how something like this works in action. So for instance, let's do, well, just in general, if I consider the Hilbert scheme of curves on my toric threefold, well, it turns out to be really great. The fixed locus is actually isolated. So this sum actually just becomes a sum over points. And so this virtual class there's nothing going on here. This is just a sum over some collection of points. And what are these points, for instance, in the case when X is C3, and I'm doing like let's say the Hilbert scheme of n points on C3. So C3 is affine, so if I want to define a subscheme, I just need to take an ideal in the polynomial algebra for 3 variables. And what you can show is that the only way for this ideal to be fixed by the torus is if I is actually a monomial ideal. So it's actually generated by monomials in these 3 variables. Okay. And so I can try to draw a picture of this, and this is going to get really rough. The following way. So I want to understand what do monomial ideals look like. And so to each monomial ideal, I can associate a collection of lattice points. So it's going to be triples of non-negative integers, which are the monomials that don't show up in my ideal. And so this is this is what's called a 3D partition, or sometimes plane partitions. And so if you look at the notes, there's a beautiful picture of what these look like that I stole, but I'll do my best to draw one of these on the board. So for instance, I'm going to draw all the boxes, again, that are not contained in the ideal. So it's going to be some kind of configuration of boxes. And the number of boxes will be precisely, in this case, n. It'll be the length of my subscheme. Okay, God help me. All right, this is more or less as complicated as I can draw on the board. All right, how about that? Yeah, okay. It's okay to laugh. I'm not going to take it personally. So that's 4 boxes, because there's that one that you can't see. All right, great. This is 4 boxes. Great. And so what this localization formula is telling me is that, let's say I'm interested in the DT invariant for the Hilbert scheme of 4 points on C3. I sum over all plane partitions with 4 boxes, and then I have to figure out what this weight term is. Yeah, so I'm going to sum over pi is going to be a 3D partition. With n boxes, and there's going to be some mystery function here, which is precisely whatever is going on here. And so this is something that's going to be kind of complicated, because it's really going to involve what the definition, meaning you have to start looking at what the obstruction space is and everything. Oh, sorry, Q. So actually, let me just, since I don't think I've said what this function is. If I imagine there wasn't any weight function at all, and I just took the generating function of these 3D partitions, and this is something that's been known for like 500 years, or maybe 200 years, I don't know, it's old, which is the McMahon function. So yeah, let me write the name down. But what we really want is this thing that's decorated by some kind of mystery rational function. And actually, if you try to write down what this function is, so let me say what it, I mean, the definition of it is actually pretty easy because since the fixed point is isolated, that stuff in the numerator doesn't show up. So I really just have to calculate this virtual normal bundle, which just means understanding the deformation and obstruction spaces as T representations. And so the idea is that to calculate W sub pi, I understand, so what were these deformation and obstruction spaces were just given by these X groups. And so I try to write this expression down as T representation. So I don't just remember their dimensions, I actually try to figure out what the character is. Representation. And so for every picture like that, there's some kind of complicated recipe for calculating what this is, and then you sum it up. And when you write it down in that way, it seems kind of hopeless. But it turns out the answer is actually quite simple. So again, so the blue means I've put in this equivariant weight, and it ends up being actually as simple as maybe one could ask for. And I think tomorrow I'll try to say something about the proof of this because it's in some sense it's actually very useful for understanding the general toric case. But the proof of this is going to be, as maybe we'll discuss tomorrow, is going to be very geometric. In principle, this is a purely combinatorial problem, but it seems very hard to imagine a combinatorial proof. So this is going to be no combinatorial proof. Once you have this, though, it's not too hard to go from this to the case of the Hilbert scheme of points for a general toric threefold. So as a corollary, it's easy to see. When X is toric, it's again just basically given by this McMahon function to an appropriate power. And then one can actually deduce the case of any threefold from the toric case. And so this goes to all threefolds using again quite delicate argument first due to Jun Lee. Okay. Are there any questions about this? I mean, I just want to give some flavor of what this kind of procedure looks like. I'll probably talk a little bit more about localization tomorrow. Okay.
I'm asking about this figure stuff.
Mm-hmm.
You can look at the Donaldson-Common homology correspondence.
Yes.
That's kind of similar to this the topology vertex versus the largest duality. There you also sound genus stuff like that.
Yeah, I mean the topological vertex. I mean, it's so to speak the Calabi-Yau specialization of all this discussion.
So the Donaldson-Common actually can be reinterpreted as this sort of transaminase side of the story, or
In the toric case, yeah, we know there's so yeah, so for toric Calabi-Yau threefolds, you can reinterpret the Donaldson-Thomas generating series in terms of this Chern-Simons stuff. Is that what you're asking? Yeah. But I don't know of any. I don't know of a version of that story for other threefolds though. Okay. Yeah, sure. So maybe I'll start off with the definition. So the definition is going to be, so the moduli space is going to consist of pairs of some kind of space of stable pairs. So E is going to be a one-dimensional sheaf, pure, so that means all its subsheaves are also one-dimensional. And then equipped with the section such that the co-kernel of the map is zero-dimensional. And so just as before, one can write down with a little bit of thought what the appropriate obstruction theory. So how should you think of this space geometrically? So beforehand, when I was doing subschemes, I had, a subscheme. And, it was maybe thick in some weird ways. And the way you should think about a stable pair in this sense is that, well, it's essentially a one-dimensional object. So first of all, there are none of these floating points. But so you can think, for instance, a curve. And then now maybe some kind of, interesting line bundle on the curve with the section. So for instance, if I had a smooth curve, for instance, the entire Jacobian of that curve would show up in this moduli space. And the co-kernel of that section is going to define some points on the curve, and that's the analog of this kind of weird zero-dimensional action that's happening here. So you're trading in the fat points and the non-reduced structure, et cetera, for some points that lie along the curve. And the conjecture, which is, I think, a kind of a much more reasonable conjecture to get your head around. So again, I'm going to define some kind of generating series for these PT invariants. But I don't do any normalization. The claim is that this equals the normalized thing on the nose. And again, in the Calabi-Yau case, this is basically a theorem. Is that? I mean, there's this kind of interesting phenomenon where, back when we first started thinking about this stuff, on the sheaf theory side, there's this, typically you always have to pick a stability condition to get a reasonable moduli space. And different choices of stability give you different moduli spaces. And on the Gromov-Witten side, there's no version of that. And for a while, this used to be viewed as kind of a defect of the sheaf theory side. But in fact, recently, this has been viewed as actually a perk, because then you can try to play off different stability conditions against each other and find relations and things like that. Okay. So the second kind of useful tool can be some kind of degeneration formalism for DT invariants. And this was mainly developed by Jun Lee and Baosun Wu. And so the idea is that, so the motivating idea, which is not actually how I'm going to use it, but still, the idea you should keep in mind is that, let's say you have some family of threefolds. Let's say you have some kind of complicated threefold X sub t, and you have some kind of specialization of it to two pieces that are maybe simpler. This is X sub t, and you specialize it to x1, x2. And it's very important that we're only considering really the simplest possible degeneration. That means the central fiber here has two components meeting transversely along a smooth divisor D, and the total space of my degeneration is smooth. So really as clean as possible. And so the idea is you'd like some way of understanding dt theory of the generic fiber in terms of these some constituent pieces. So you want some formalism that allows you to just, so ideally x1 and x2 would be things you've already understood, and then you put them together and you're in business. And so the first question is actually, what do I mean by studying the dt theory of a pair? Because under that degeneration, I have x1, but it's being glued along some divisor d. And really, both x1 and d should show up. So what is the sheaf theory of a pair like this? And again, there turns out to be a great answer to this question. So yeah, before I start just racing into definitions, let me just say why the sense of being useful beyond just the possibility of some kind of degeneration formula. One of the issues that we have in studying sheaves is that, unlike stable maps, stable maps have all this kind of extra structure because we have evaluation maps and we have forgetful maps, and we can play those off against each other. And we don't have really any analog of that in the sheaf theory world. It took us a lot of work just to construct insertions using this kind of Chern characters and things like that. What's nice about these relative spaces is that they actually naturally carry some extra structure. And it's structure that's very similar to structure that we have on the Gromov-Witten. And that fact alone already has ended up being extremely useful. So, I mean, I'll try to explain that in some examples tomorrow. But, I mean, in some sense, these spaces by themselves are useful independent of the actual gluing formula. Okay, so what is the setup? So x is some smooth threefold, d is some smooth surface inside it. And what I want to do is I don't want to consider all subschemes of x. That's what I did before. I want to only consider subschemes that meet d nicely. The way we say that, I have some ideal sheaf, I sub z, and I say it's a relative ideal sheaf if I take the canonical inclusion and I tensor it with O sub d, it stays injective. So if this sequence is still exact. See, in general, it may not be, right? There could be some kind of tors that come to the left that'll mess everything up. And what this means geometrically is just that if I have my subscheme, well, I can have some kind of reduced points or some embedded points or some floating points, and I want those to stay away from D. Not only that, I mean, I could have an entire component that lies inside D, and I don't want that to happen either. So what this means is that no embedded points or components lie on D. So this is an open condition. So it defines some kind of, some open subset of my original Hilbert scheme. But it's sure not going to be proper, because I can just take one of these floating points out here and then start moving it to D. And the limit in the Hilbert scheme is obviously not going to be in this open space anymore. So the idea is that I want to find a new compactification of this open subspace where this property is always true. And the geometric idea is that if this point is chasing after D, then I let D run away. So I compactify by allowing X to bubble. So what that means is that, let's draw slightly simpler geometry. So again, I have some point here. And I have a family of subschemes where this point is chasing after D. The kind of limit that I'm going to allow is going to be a reducible threefold that I get by degenerating to the normal cone of D. So it's going to be X, and now here I've attached a projective bundle over D. So this is now a reducible threefold. Sorry. And if I study what happens to this family of subschemes with this in the central fiber, I get something that looks like this, where now this floating point is now away from the proper transform of D. So this is the new D out here at infinity, which is just the proper transform of my original family of divisors. And in this limit, the point has still stayed away from it. Now, in order to get something separated, I need to be a little careful about when I consider two such subschemes the same. So if I have two, ideal sheaves, I want them to be the same if they differ by an automorphism of this threefold over my original base. So that means I'm allowing a C star scaling. I guess maybe this is the way to do it. And, well, okay, fine, I solved this problem once, but what if there are more points that keep on going chasing after my divisor? Well, then I allow multiple bubbles. So in general, my moduli space is going to consist of a pair first given by a choice of target degeneration. So K here is the number of bubbles that I'm allowing. And then an ideal sheaf on that choice of target with the property that I sub z is a relative ideal sheaf. Which just means this condition here, not just at this divisor all the way at infinity, but also on the singular locus. That means on D. And so again, geometrically what that means is that all this kind of, all this embedded points or whatever stays away from all these copies of D. And also, along D, these two subschemes have to match up correctly. Finally, I need something to make sure that I can't keep on bubbling forever. So I also require a stability condition, which just means that the automorphisms in this sense here, the automorphism group is finite. Okay. So there's a lot going on here, but I mean, the point is that you just want to keep on imposing this kind of transversality condition, and the way you do that is by being flexible about what you mean by X. And so the main theorem, and so let me just state the main theorem and then two pieces of information, and then I'll continue tomorrow, is that, well, okay, so this is, first of all, this is actually a proper DM stack. It's no longer a scheme anymore like the usual Hilbert scheme because I've got these automorphisms coming from these C star scalings. And it carries a, a two-term perfect obstruction theory, all the stuff that we want. So we can again talk about the virtual class and define invariance this way. And the virtual dimension is just as the same as it was in the usual case. So let me just say two facts about this thing, about this space, which is the structure that this space has that the usual Hilbert scheme of curves does not have. So what is the extra structure? So the first is that unlike the usual Hilbert scheme, I actually now have an evaluation map, which is that I can take this space of relative ideal sheaves and I can get an element of the Hilbert scheme of my divisor D. The reason why is that by construction, IZ is always intersecting D cleanly. And so if I take just the restriction map, this actually behaves well in families by construction. So when I'm doing this bubbling, I'm always intersecting it with the copy of D that's furthest away. So again, this is going to be a map really from this space of relative ideal sheaves to the Hilbert scheme of points. It's going to be some number of points of my surface. And I'll come back to this tomorrow maybe, but what's nice about this is that the Hilbert scheme of points on a surface, of a smooth surface, is itself, unlike the Hilbert scheme of a threefold, this is actually a smooth projective variety. And we know basically everything we want about its cohomology. So understand the cohomology very well. And so then by pullback, let's call this mapping G. By pullback, then we get a lot of classes here that we understand well. Okay. And so the second piece of structure is a little more subtle. And again, it's one of those things that seems kind of idiotic. Is that I also have a forgetful map. Or take the space of relative ideal sheaves, and I just forget the sheaf. So this consists of a pair, a choice of target, and then an ideal sheaf on that target. And I'm just going to remember what my target was, how much I've bubbled. So there's some stack, actually. There's some Artin stack that parameterizes these target degenerations. And it's kind of a weird object because it's got a point for every value of k. So it's got a point for 0, 1, 2, and so on. And those other points for k bigger than at least 1 all have automorphisms because it's the automorphism group of the point corresponding to xk is precisely c star to the k. So this is a little strange, but it turns out actually that you can think of this as pretty familiar. So let me say this is smooth. Well, first of all, k can keep on going. So this stack is really of infinite type, but for any given discrete invariance upstairs, we're only going to see a finite piece of it. So that's not such a big deal. But it turns out this stack T is something pretty familiar. So let me say what it is, and then I'll shut up. So if I consider the stack, so that's a super curly M, M03, which is supposed to be a stack of genus 0, 3-pointed, I think what YP called pre-stable curves. So that means nodal curves and the points stay away from the nodes. Okay. And sitting inside this guy, okay, so this is some huge infinite type stack, and inside it we have an open substack which consists of curves that look like this. It's going to be a chain of rational curves with the first 2 points here and the last point here. So it turns out this is an open condition. Let's find some open substack here, and these are actually the same. And the idea is the number of chains is corresponding to xk. Each of these chains, each of these deeper chains has exactly a C star worth of automorphisms, so it matches up, and you can actually make that more precise. And so why is this useful? Well, I mean, we have all, this is some kind of unwieldy object, but we do have some kind of nice cohomology classes on it, psi classes and boundary classes, and we have some relations among them. And so I can pull them back via this map and get identities upstairs. Okay, so let me stop here. I'll be using that tomorrow, I think, ideally. So both of these maps are going to show up, and we get to play them off of each other and play them off of localization.